Our next speaker would be Fabian Ferrer from Tokyo. He'll be talking about continuous variable entropic and uncertainty relations in the presence of quantum memory.
Thank you for the introduction, and also thank you for the organizer giving me the opportunity to present our work here. So I will talk about continuous variable entropic uncertainty relation in this presence of quantum memory. I will explain what this means. So this is joint work with a bunch of people. There's Mario Berta, Volker Scholz, and Matthias Christandl at ETH Zurich, and Marco Thomas Michel at CQT in Singapore. So let me just start with introduction and motivation first, and then I will show you what I will cover in this talk. So we have already seen different types of uncertainty relations. So there was nice talks by Cyril Branciard and Patrick Coles about this first scenario where you have actually subsequent measurements. This was actually what Heisenberg considered in his famous paper. So then we have kind of a measurement disturbance trade-off here. But what I will talk today is about these preparation uncertainties. So we look at the observable, or the measurement performed on the same state here. We have two measurements and they are applied on the same state. And then we can say that if they are actually not, if they don't commute, that they actually, it cannot happen that S and T are both sharp. And maybe let me go on with some history. So because we are talking about position and momentum operators later, about continuous measurement. So this was actually where it started with Heisenberg's uncertainty relation shown by Kennard in 1925. Here that the variance of the position measurement times the variance of the momentum measurement, that this is actually the product is bounded here. This was then later improved in 1975 by these two papers here by using not the variance but the Shannon entropy of the continuous distributions here. And you get also a bound here. And a major breakthrough in the finite dimensional case, when one looks at finite dimensional system and also finite number of outcomes, was this result by Marston and Uffing. There they showed that if you have this let's say, non-degenerate observable S and T, and we look at and here we have now the Shannon entropy of these discrete distributions, then this sum here can be bounded by a constant, and the constant not depending on the state. And this constant is just given by the maximal overlap of these eigenstates of the two observables, Sk and Tl. So, but recently one actually extended this relation, includes quantum memory. The interesting thing is that one can then combine things like entanglement, which is important from quantum, which is one of the important properties of quantum mechanics, with this uncertainty principle. And the situation looks the following. So now we actually have more parties. There are different ways how to state this uncertainty relation. I'm considering here the tripartite version. So we have three parties. Here is Alice, and Alice is measuring. And then we have Bob and Charlie. And we are interested about quantifying the uncertainty of this observable S, given Bob's information here stored in a quantum memory, and the uncertainty Charlie has about the outcome of this measurement. And to see that this actually still allows kind of a bound on these uncertainties, we look at a simple example. And the simple example is where Alice and Bob, we have this preparation, and Alice and Bob share maximum entangled qubits, and Charlie is completely uncorrelated. And then Alice is just measuring either in the C or in the X spaces. And what turns out, of course, because Bob is maximally entangled with Alice, he can, certainly predict the outcomes of this observable S. So we assume that they know which observable is measured. But for Charlie, on the other hand, we have that he actually has no information about this outcome here, in the sense that first he's uncorrelated, but also due to the monogamy of entanglement, we have that actually that for Charlie, this states on the other side looks like the maximally mixed state. So we still get kind of this uncertainty relation if we actually consider these two parties induced quantum memories. And one can make this precise. This was this really nice paper here, that if one actually looks about conditional entropies, and this is the conditional von Neumann entropy, And it's defined in the following way. We just take the entropy. I mean, we look at this state here. This is the kind of a classical quantum state. We assume that this S, this basis here, is orthonormal basis, and this rho bs are actually the conditional state if the outcome of the measurement would be S. And this is the probability distribution of the outcome of the observable. So if you look at this state, then we can just compute the von Neumann entropy of the state SB and of the state B. We take the difference of these two, and we get the conditional entropies. And if you use this measure here, then we get this bound here. And this bound here, I mean, this same like in the Maass-Nuffink inequalities, ODC is exactly the same. And the good thing is now that we actually have, using kind of these conditional entropies and also this entropy measure, that we actually have some applications. So, because these quantities have some operational meanings in the information theoretical sense. So one application, one easy application is in quantum key distribution. So if we regroup it a little different, we now call Charlie Eve, because it's the eavesdropper. Then we can look at the following scenario. It's also tripartite. We have here a side channel here. I mean, QKD protocol is kind of Alice sends the state here, Bob is measuring, and then from this measurement data, they want to extract the key. And what we want to have, what they want to do is kind of to bound the information Eve has about this outcome of this observable. And I mean, it's clear that this is exactly the setting what we study, or I showed you before. So we can just use this inequality to bound the information. So now the information is now measured in the asymptotic limit by using these von Neumann entropies. And this has successfully been used for discrete variable protocols, but also for continuous variable protocols. But so what we're doing now, but so far this was always, I mean, for a finite number of outcomes, or even for finite dimensional systems. So what we want to do in this case, because it's also historically it started actually the discussion with position and momentum measurements. So these are continuous measurements, and what we wanted is kind of to extend this uncertainty relation to position and momentum measurements, or more generally, we showed it for arbitrary continuous outcome measurements and arbitrary infinite dimensional quantum memories. So, of course, it depends. I mean, one has different uncertainty relation depending on the measure appearing in defining this kind of the information one has about the outcomes and so on. So the measure we concentrated on is the differential condition for Neumann entropy, which is, I guess, familiar to most of you. And it's actually the one appearing often in physics, statistical physics, but also if one looks at the asymptotic limit in information theory. Another one, what we consider is the differential conditional min-max entropy, and these are really important for finite size QKD. This is actually when we really want to have a security proof, then we have to use these kind of measures. So that's why we have chosen this, we focused on these two. And maybe let me mention some related work. There was a work by Frank and Lieb, where they also showed a similar uncertainty relation by using a somewhat more restrictive definition of this differential conditional for Neumann entropy. And in the case of min and max entropies, there was something shown for finite number of outcomes and infinite dimensional, quantum memories. So in the following, we only consider the case of differential condition for Neumann entropy, because I guess you're more familiar with this one, but we showed the similar things also for this in the paper mentioned also at the end. So now the outline of my talk is then I will first kind of focus a little bit on a continuous variable system. What's my approach to continuous variable system? Then we will introduce these differential entropies, and then consider the uncertainty relations. So maybe the most prominent continuous variable system in quantum information processing is using kind of the quadrature of the electromagnetic field. So they can be accessed by using Homodyne detection. Homodyne detection works as follows. So we have here the signal we want to measure, and we overlap with with a strong local oscillator here, which is phase locked with this one, and then we overlap with a balanced beam splitter, and then we have here this photon counter, and then we subtract the signals. So as we saw in this morning, one often wants to encode actually, especially theoretically, the information in only one mode, so we want to filter out one mode. And if you look at this one-mode model, then it's equivalent to the harmonic oscillator. So it's an infinite-dimensional Hilbert space. And if you look at this measurement here, so as I said, if the phase log is, they have the same phase here, then we actually and consider a measurement with the same phase and one with pi2 difference. Then if you look at the commutator, then we have exactly this canonical commutation relation. So we have position and momentum operators, and hence also continuous spectrum. But so in the following, we look at two different measurements. So one is the ideal measurement. Of course, this is kind of, it's ideal because it's not, one can never achieve or perform such a measurement in the lab. So ideal in the sense that we assume that actually our outcome is an element of the real line, so it can be any real number. And we also here now include this quantum memory, because we are afterward interested in having this outcome based, given this quantum memory. And then, of course, if you have this outcome here on the real line, then this induces kind of a post-measurement state on this memory here. And the whole system here can be described by a probability distribution and this continuous ensemble of states. And the following, I just denote this by this rho xb. In a more practical scenario, of course, what happens is that we have a discretization of our outcomes, our measurement device, and so on. And this is the following case. So what we actually look is like we have here kind of, we can think of this ideal measurement, but then if you look at our measurement device, we have a natural discretization, and the outcomes are now discrete. But it is also introduced, we also have here this post-measurement state in the memory. And if we actually, the way how we discretize our system is we just divide the real line into intervals of same length delta. So, and we denote actually this random variable which comes out of this system here by x and with this lower subscript delta. And then, of course, we have a discrete probability distribution and a discrete number, but it can be, just a countable number of post-measurement states. And of course, they're related. We want to actually, this is kind of a coarse graining of our continuous outcome measurement. So what we want to do is we want to actually minimize our delta to approximate to this measurement as good as we can. And then, of course, in the limit, we should actually come here in this sense. But practically, we're always here. So, but if one then looks at the operational measures, what one wants is that they're actually kind of continuous in this limit. Or this is my perspective, because we want a kind of operational characterization of some information theoretic task, for instance. Then we want that we can actually use this simplified version with this continuous outcome to approximate this version, which always happens if we do it in the lab. So this was my, this is the two measurements we look at, the discretized and the continuous in the following. So let me come to the differential conditional entropy measures. So motivated by what I just talked about, this approach to these continuous measurements, what we want is kind of a unified definition holding for discrete and for continuous outcomes, and also that we have, if you look at this finer and finer coarse graining, that they actually converge to each other. So that we have actually this continuity for delta to 0. And also, we are interested also in application in QKD. And in that sense, we want to have no restriction, because we want to actually, we don't want to restrict to anything, states or setting or the quantum memory or anything. So the way how we define the conditional entropy for Neumann entropy is the following. So the usual definition, maybe, from standard textbook, is kind of this, taking this subtraction, of these two entropies, as I showed at the beginning. So this is actually this classical quantum state with the post-measurement states, and here this orthonormal basis. And then one just computes the von Neumann entropy of this thing, which is given by trace rho log rho. But you can also write it in terms of the quantum relative entropy, given like here. We just sum on this quantum relative entropy, and this quantum relative entropy is this guy here. And the good thing about this quantity is that it's really well studied in infinite dimensions. So this was, definitions on by Araki, and then there was studied by Dennis Petz and other people. And so there's a whole machinery we could could use to actually, I mean, for dealing with these entropies. And then, I mean, it's just straightforward. We just take the sum and replace it by integral. But, I mean, of course, this can be now an arbitrary measure, but in the following, we only just consider two special cases. If x is actually the real line and mu is the Lebesgue measure, then we can just, I mean, then it's just simply given by this, doesn't look different, and we call it a differential entropy, because Shannon also already introduced this entropy of a continuous variable given like this, and of course, I mean, if one looks at this special case where this B system here is trivial, we actually end up exactly with this definition. So, and in a discrete case, it's actually we recover this situation here of, I mean, this is then just a point measure, discrete point measure, and then we just allow up to infinite sums. And in this case, where it's discrete, we use capital letters. So, and now one of our main results is that we actually have this approximation theorem. So if you look at this, I mean, the discretization of delta and then the corresponding, I mean, conditional entropy, then if we take the limit here, regularize it with this log delta, then we retrieve here the conditional, differential conditional entropy. I mean, and the assumptions are very mild and kind of, I mean, can be stated in terms of entropies. So we just have to assume that this is not minus infinity. So I have to say that these differential entropies are different because we have to regularize them with this log delta term. So, and this goes to minus infinity, this goes usually to plus infinity. They meet somewhere, and they can be positive or negative. So we have to exclude this thing. And this is just, can be also, for a physical motivation, this always holds if you have finite energy. I won't go in the proof of this statement, so it's mostly based on some approximation theory for the quantum relative entropy, which is due to Petz and co-workers. So maybe, I don't know, quick, maybe to get a feeling about this thing. So why we need this log delta term in this scaling here. So we can think about this approximation. If you have a continuous function and if you let this delta go to 0, then the function, at some point, the function looks almost constant over all this delta, and then we can find this region of constant, kind of where the function is constant, and then we can look at the entropy in this region. And if we compute this, this V is just the volume or the length here, and then we can compute this, and what we see is that this actually goes like the probability to be in this region times the log of delta. Summing up over all the regions, we actually have this log delta we have to add in order to regularize the quantity. Okay. Since I'm running out of time, let me go now to the uncertainty relations. So the way how we proved our uncertainty relations is we started actually with finite outcomes, because there we can use all the properties of these entropies, and I mean it's mostly technical, and then what we did, we showed this version for kind of non-normalized measurement, and then we actually we made the transition first to a finite infinite number of outcomes. So already there were some problems we had to deal with, and the outcome was this uncertainty relation if you have these finite precision measurements. Because if we divide the real line in intervals of length delta, we still have an infinite number of outcomes, and so we have to deal with this infinite case. And in that case, what we found is kind of this relation here. So we have this is just the entropies with this spacing here delta, and then this constant here, which actually bounds our entropies here, is given by the overlap. So this is actually in the same like in the Mass and Uffing. If one just has these overlaps of the measurement operator, and this Q delta K is just kind of if we use the spectrum measure, I mean, on this interval of length delta. And I mean, of course, I mean, this must kind of be independent on how we discretize. So this is, of course, translation invariant, because although these quantities are not translational invariant. But this must be, because we can just apply unitaries. Like.
You said the Q was a spectral projection?
Yeah.
The
Oh yeah, we just take the operator and take the square root. Because it's a positive operator, and then we can take the square root. Yeah, of course, in this case. Yeah, sorry, yeah. You're completely right. In this case, but I mean, this also holds if it wouldn't be if it's just a positive operator valid measure. So then, sorry, yeah, this you can think about. And we can leave out here the square root, sorry. Okay, and then, I mean, let me maybe just show you how this behaves. So this is the plot of this minus log C delta. So this is the variance of the vacuum. So if you go below the variance of the vacuum, it actually increases quite fast. And on here we have the plot for large delta. So this is around, I mean, almost everything of the support of the vacuum is confined here. So this is a minimal uncertainty state. So of course, if we're in this region here, then we can actually prepare minimal uncertainty state. So we have to actually assume that the uncertainty goes to 0 here. And this is what happens. So this is the C of delta. And if you take the log, then it's 0. So, and the differential version we now just get by using our approximation theorem. So we start with this discretized version, and then we use this approximation theorem for delta equal to 0. So this one here, and then what we get is straightforward this inequality here. So this in general is kind of the one I showed at the very beginning with outside information, but now we have a factor of log 2 pi than log e pi before. And of course, then it's a natural question, because we know the other one is tight, and now we have actually this, the bound is actually lower than in the other one. The natural question is this also, this uncertainty relation sharp? So this means, is there a state where we have equality? And as I said, I mean, we know that in this case, I mean, this one is known here, and this bound is actually tight. So what we know is that we have to use our side information. And what I can show is that if you take a EPR state, so the famous paper of the Einstein-Podolsky-Rosen paper, so where we have 2 times this position momentum system, and then we have a state where the position measurement on the A system, let's say here, and on the B system, they're maximally correlated. So they're perfectly correlated. Of course, this is not a state, but we can think about this is a limit of a state. So if one looks at this 2-mode squeeze state here, they have actually, this is the position, this is the outcome of the position measurement of Bob and here of Alice, so they're actually quite correlated. Enhancing our squeezing, then this gets narrower and narrower, and the limit for squeezing to infinity, this gets exactly these EPR states. And what I can show is that in this limit, actually this goes tight, so that we have here equality. And what we also see that we don't need we only need one quantum memory. So, and it's also actually practical in the sense that this gap is actually closing exponentially in the squeezing strength. So that's shown here, and maybe for I mean, more experimental, I mean, what we can achieve in the lab, I mean, there was a recent paper by Tobias Eberle from Hanover and other cohort. They showed a 10 decibel squeezing, and this actually corresponds in my notation here to this line here. And in this line here, actually, the gap is almost 0. So it's actually experimentally, we can go really to 0 here. So let me finish with some comments about this sharpness of different uncertainty relations, because I think it's really an interesting thing what's going on, and actually I have to admit I don't understand it at the moment. So we have that this relation here holds. But this is also, I mean, it's easy if this X is a classical side information here. So this is the classical memory, then this kind of straightforward implies just this relation. And then we also have another one actually shown by Frank and Lieb just recently in 2012, that we have this for also unconditional entropies, that if you have this log 2 pi factor, and then we add here the mixedness of the state, this kind of measure of the mixedness of A, the system A, then we are also sharp. And we're sharp actually for the thermal state if we let the average photon number go to infinity. And this is actually the same behavior we have here, because you can think, I mean, this EPR state, I mean, if we purify this state here, we actually get the EPR state. And then we actually end up with we can just take here a trivial side information C, and then this still holds, of course, and then we actually retrieve our tightness result. So these are kind of, this uncertainty relation have kind of capture same, characterize kind of same behavior, while this one is kind of different. So this is maximized for these poor Gaussian states. And also interesting that actually, yeah, if we're measuring out this quantum memory, we go to this setting and we have kind of here jump. I don't know, I mean, if this is actually operational or not, because we don't know what this measure really means here, this conditional entropy measure. So let me conclude. So we showed, we introduced this, general kind of definition of differential condition for Neumann entropy, and we showed this approximation. We also showed this, we also introduced this differential min and max entropy and showed the same approximation for this kind of entropies. And then we showed this uncertainty relation for coarse grained on continuous measurements. And in the case of min and max entropy, they're actually tied for finite and infinite precision. In the sense of for a finite delta and for delta to 0, they are actually already tied without quantum memory, which was already known before. And then we showed sharpness in the continuous case for the version with the differential condition, the min entropy, so with these EPR states. And maybe some outlook. One thing is, I think it's interesting to understand this difference and this different characterization of this various uncertainty relation to kind of find out what actually happens in this case. Then also, I hope there's a lot of application in quantum cryptography. One is in continuous variable QKD. There was already applied such a relation, but there one used discretized actually and finite number of outcomes. But maybe this one can be now improved because we don't have to introduce this discretization. And also, what I learned is that they maybe have application in the noisy, in the noisy storage model here. And yeah, another thing is like about this differential conditional entropy measure. So that's actually not so clear what they express in operational sense. And our approach in this work was that we look at the infinite, the limit of finite discretizations. So with that, I'd like to thank you for your attention.
Maybe one quick question we have time for.
So I didn't quite understand the memory part of the thing. So is the system C understood to be the memory? So if I understand the system correctly, A and B share an EPR pair or some maximally entangled state, and both A and B perform measurements, but C also performs.
Oh, no, then it's a misunderstanding. Only A performs measurement. So, and you actually start with a shared state between Alice, Bob, and Charlie, and they can be arbitrary entangled. That's arbitrary. And then I only measure the Alice side, and then I actually look at the uncertainty with respect to Bob's quantum memory and Charlie's quantum memory.
Ah, I see. So it's a tripartite shared state that is
exactly. Yeah.
Okay.
Yeah.
Okay. Thank you.
So let's thank the speaker.